Hello students, welcome back. Let us resume our discussion in section 2. We completed all the required components there, but there are still some additional topics that I'd like to talk about. Please recall that we defined the derivative using either average rate of change expression or Newton quotient expression. Either way, they're equivalent. And then we defined the derivative function using this latter expression, this Newton quotient expression here, and replace a by x, and then let x move around, then we get the derivative function. We went through all those definitions. On top of those, let me talk about some terminologies here. The process to find the derivative refers as to differentiate. So this term, to differentiate, is a verb, and that means to find the derivative. We use the same term for derivative value f prime of a, or the derivative function f prime of x. So the process to find the derivative function, or the process to find the derivative value, both are referred as to differentiate. Also, a function f is said to be differentiable if the derivative exists, but first, differentiable at a certain x value when the derivative value x prime of a exists. We can consider this term differentiable, or to differentiate is possible. It is possible to differentiate at a single point. That means this limit exists. In that case, we say f is differentiable at x equals to a, and also we can do this for a function. In that case, we have to have a domain, not just a single value, so we consider that in an interval. A function f is said to be differentiable in an interval from alpha to beta if the derivative function f prime exists for all these elements in the interval. So for every x between alpha and beta, f prime of x, this limit exists. So either way, we use the same term, differentiable. The derivative function exists, or the derivative value exists. In any case, remember those terms, to differentiate and differentiable. As for the derivative calculation, or differentiation, the noun form of the same verb that we talked about, to differentiate. And we went through a couple of methods there. Newton quotient method, calculate the limit, or average rate of change method, and calculate the limit. Those are all differentiation problems. Define the derivative. Okay, all right. Now, even more about those terminologies. Here's a big theorem. If f is differentiable at a certain value, x equal to a, then it is continuous there. So differentiable means a bit stronger than continuous. In other words, if a function is not continuous, then there's no chance it can be differentiable there. Derivative does not exist. It cannot exist. But not necessarily vice versa, as a matter of fact. A function is continuous there means there's a chance that derivative exists. May or maybe not. Well, that aspect will be discussed a little bit more in the next section. For now, let's prove it. This is what you want to prove. If the derivative exists, which means if this limit exists, then function is continuous. This limit exists and that value is the function value. So this limit exists and we call it f prime of a. Then this limit exists, and not only that, that limit value is the function value f of a. Okay, let's prove it. First, let's use a trivial limit rule to re-express the conclusion like this. So we want to prove limit of f of x is equal to f of a, but limit of f of x can be rewritten as f of a plus limit of f of x minus f of a. What do you mean by that? Well, if you use the trivial limit rule, the right-hand side is this, and then that's f of a plus limit of f of x minus limit of f of a. But then again, f of a is equal to limit of f of a because f of a is constant. So this one and that expression there, they cancel each other out. And we just get this one here, which is the left-hand side. So let's begin with not just limit of x is going to a f of x, but rewrite it like this. And then let's work out the second limit. How can I work it out? We're going to multiply and divide by the same thing. Multiply by x minus a and divide by x minus a and apply the limit rule. Limit of this quotient times limit of this x minus a. Make sense? Divide and multiply by the same thing, so no change, and then use the limit rule. This red limit and this blue limit. Now this red limit is a derivative, and the blue limit is a minus a, so that's 0. Do you see that? This is a derivative, red limit is a derivative, blue limit is a minus a if I plug in x equals to a. So f prime of a times 0, any real number times 0 is 0, so this part just drops out, you just get f of a. So what's the conclusion? The limit is f of a. Yes, we got it. We have the proof of the continuity. So the conclusion? If a function is differentiable, in other words, if the derivative exists there, then the function is continuous there as well. Not necessarily vice versa, however, but that aspect will be discussed in the next section, and we're going to approach graphically there, by the way. One more thing here. What if the derivative doesn't exist? In that case, this entire process can break down. Here, f prime of a times 0, so something times 0 is 0, so this entire thing drops out, so that this limit is just f of a. Well, that doesn't really work out if f prime of a is not a real number. Anything times 0 is 0, yeah, but that means any real number times 0. What if this red limit goes to infinity? Infinity times infinitesimal may not go to 0. It may go to anything or may not go to anything at all. So x minus a, x is getting closer and closer and closer to a, but not equal to a yet. So this is actually a non-zero quantity. And this one here, excuse me. This quantity here, blue, this is a non-zero quantity. This expression here this is a real number, but upon taking the limit, this red may blow up to infinity or even worse. In that case, this limit rule, limit of this red times blue, is red limit times blue limit. That rule may not work. If this limit does not exist, then this limit rule may not work. That's why this thing is working the way it is when the derivative exists, not necessarily every single time. So you cannot use the same argument to prove that every function is continuous, because it is certainly not true. Okay, so much for this big theorem and the proof. We have some time left, so let's discuss some historical aspects here. There are many different derivative notations developed by a number of people in a number of different cultures. One of the most widely accepted notation is Lagrange's notation, the derivative f prime of x, and take the derivative of this function again, the derivative of derivative. We have the second derivative function, f double prime, and the derivative again, then f triple prime, and then if you have too many of those, then parenthesis n, so nth derivative. This notation was invented by Lagrange, and he is an Italian-French mathematician, and you can find out about this Lagrange in Wikipedia page like this, for instance. And that's French notation. And this notation here is by Leibniz, and it is German notation, and I'm talking about this person here. The first expression, infinitesimal difference over infinitesimal, that's understandable, but second derivative, third derivative, nth derivative, why do we have nth power here and there? It's hard to follow. Every time I use this notation, students actually struggle, but I have no choice. You have no choice either. It's too late to change anything, you just have to learn both. Now this is my personal favorite, Euler's expression. Euler is a Swiss mathematician, this person. And the derivative, well, let's just put d here. And derivative computation once more, d squared, d cubed for the third derivative, d nth power for the nth derivative. And this expression goes very well with computer programming, actually. So almost all computer algebra systems use some version of Euler's notation, not Lagrange notation or Leibniz notation. This one is most popular in technology. Finally, the first, Newton's notation. And this expression, as a matter of fact, phased out even in England. But this one has historical importance. It was the very first. Newton had developed a theory of calculus before anybody else. He didn't prove anything. Leibniz proved quite a bit, not all of it, but quite a bit. So some people give more credit to Leibniz, especially he or she is more of a pure mathematical side. But historically speaking, and also in applications or physicist point of view, Newton was done first, and then Newton's contribution was bigger. Me, I'm somewhere in the middle. I already told you that my favorite is Euler's. Anyway, here's some historical remark, and that's why we have different notations for the same thing. Okay, so much for section 2. Let's meet again in section 3 later.